CO bonds. We started talking about the CO double bond in terms of esters, amides, carboxylic acids, etc. And most of those reactions were reversible. And we were using relatively weak nucleophiles like alcohol or water in a hydrolysis. So it's worth stepping back and thinking about these irreversible nucleophiles that we just learned about. So hydride reagents like lithium, aluminum hydride, sodium borohydride, and also essentially alkyl minus equivalents like the Grignard reaction and alkyl lithiums. So how do these irreversible nucleophiles react with esters and the like? Let's talk about what happens if I were to treat an ester with lithium aluminum hydride. Lithium aluminum hydride is a great nucleophile. This is a really high energy sigma bond. It acts like H minus, even though it technically isn't. But this is going to transfer that bond to this carbon, and then those electrons get pushed up to oxygen. We have a tetrahedral intermediate that looks just like our last reduction tetrahedral intermediate. But now I've got a leaving group here. So if this O minus leaves, I can kick out O minus there to get that. So how do I know it's a leaving group? Well, we can compare this with that, right? So here I've got an O minus, here I've got an O minus, right? So right there, it's not like I'm making a really strong bond or a really strong base from a really weak base. These are essentially equal in basicity. So which is more stable? Actually, this is more stable because the carbon-oxygen pi bond is actually very, very stable, right? We talked about that really briefly at the beginning of Organic 1. But the carbon-oxygen pi bond is pretty stable. So this is going to be a fast reaction. Again, I start with a O minus, I end with O minus, so that's a reasonable step. So cool. Here's my problem. Aldehydes are way more reactive than esters, both from a steric standpoint, right? This is now not very crowded at all, whereas this is a little more crowded. And even an electronic standpoint. Even though this is withdrawing electrons through the sigma bond, these pi orbitals are conjugated into the pi bond. So we'll lay out the order of reactivity in a second. But suffice it to say that aldehydes are way more reactive than esters. We will never stop here, because as soon as we make this, this will react with lithium aluminum hydride in exactly the same way we talked about earlier to get us to the alcohol. Lithium aluminum hydride will add 2 equivalents of hydride to the ester. We'll start with an ester, we'll end with a primary alcohol, CH2OH. Sodium borohydride won't react with esters. It's not powerful enough. Sodium borohydride will only react with ketones and aldehydes, but lithium aluminum hydride will reduce esters all the way to alcohols. The mechanism for reaction of Grignards with esters is the same story. Notice I just carefully erased all the H's in that last reduction step and put in methyl groups, right? So if I have methyl magnesium bromide, it's a great nucleophile. It's going to react right there. Again, high energy, sigma bond is my nucleophile, this is my electrophile. I'm going to make a tetrahedral intermediate that's not going to last because it's got a leaving group, right? So O minus comes back down, kicks out a different O minus, and now I have this ketone. Ketones, like aldehydes, ketones aren't quite as reactive as aldehydes, but ketones are still more reactive than esters. So it's not going to stay there. It's going to react again, right? Because the LAH will prefer to react with ketones over esters. And so we will end up with this thing where now my Grignard is added twice. Instead of getting a primary alcohol, now I have a tertiary alcohol, right? Carbon, carbon, carbon on my CO. These irreversible nucleophiles add to esters twice. If it's H minus, I end up with a primary alcohol. If it's some alkyl minus, I end up with this tertiary alcohol. And it will essentially react the same with acid chlorides and with anhydrides. Those have leaving groups that are even better than this. But we probably wouldn't do that reaction simply because esters are easier to work with than acid chlorides or anhydrides.